All right, today we are starting on looking at the convolution on the graphs from the spectral perspective. Last session, we'll look at the basics of, not last session, but the previous lecture. We discussed how we can take Fourier transform and redefine it into the graph domain, and then want to use that in order to define convolution on the graph. So just to be on the same page, let's have a few slides reviewing this. So Fourier transform, we said that our motivation for looking at the Fourier transform is that we want to define convolution in the frequency domain as a dot product. So we don't want to do that convolution in the spatial domain. We can take information from spatial domain to frequency domain using Fourier transform. So Fourier transform takes some essentially signal, we show it with F here, and expand it into using some Fourier bases. So Fourier bases here are these exponential terms, e to the 2 pi isc here in this integration. Now, in this relation, this means that we're expanding the basically signal F into bases, Fourier bases, and the output is called Fourier coefficients. Now, we can take these Fourier coefficients and using them reconstruct the original data. So this means that we want to map project from the Fourier domain into the original space. And we can do that using inverse Fourier transform. So inverse Fourier transform takes these f hat at different frequencies, and then it returns you the original data using this relation. Now, we're going to look at where these essentially basis for the Fourier transform is coming from. The basis for Fourier transform here, this exponential term, is essentially the eigen basically functions of the Laplace operator. So eigenfunctions are essentially eigenvectors of an operator. This eigenvector, it's the same thing. And we see that our Laplace operator, which is the divergence of the gradient of some function f. If I write this down, I will see that I have here a term where I have this term on both sides, and I have essentially an eigendecomposition of the Laplace operator.
So what are the bases?
What are bases?
Yes.
So bases, you mean the eigenvectors? So
the basis of Fourier domain.
So these exponential terms.
The sentence about the basis of the.
Oh, we can show that basis of the Fourier domain are eigenfunctions of the Laplace operator. So we have Laplace operator here, delta, and we're showing that if I write this down, I will get the Fourier transform, the basically basis for the Fourier transform.
So what are the bases? What's the concept?
So we just take the Laplace operator and we show that the eigenfunctions of the Laplace operator are the basis for the Fourier transform. So these basically bases that we use for the Fourier transform are eigenvectors of the Laplace operator.
Okay.
So we want to now use that and find an analog in the graph domain. That's the idea. That's why we're looking at this. And if you remember from our fifth lecture, we said that Laplacian matrix is analog of the Laplace operator for the graphs. So now we use this analogy And we want to say that these eigenvectors that we have for the Laplace operator, we can do the same. We can do a eigendecomposition of the Laplacian matrix and find those eigenvectors and use those eigenvectors as the basis for the Fourier transform on graphs. So we are just finding an basically a corresponding essentially basis for the graphs that we can use for graph Fourier transform. Now that can be shown as we said using eigendecomposition of the Laplacian matrix. And let's say that I have this Laplacian matrix L. I find its eigendecomposition. I write it like this. And then these eigenvectors, UL, are eigenvectors of the Laplacian matrix. And these eigenvalues, lambda L, are eigenvalues of the Laplacian matrix. So these eigenvalues give us a notion of frequency, as we discussed in the previous lecture. And the ULs, the eigenvectors, give us a notion of basically basis, using which we can take essentially some signal defined on the graph. We call it spatial or nodal domain. And we can represent that in the space of the eigenvalues of the Laplacian matrix. We call it spectral domain. This spectral domain is analog of the Fourier domain for the graphs. So what we can do is that we have some traditional signal processing essentially tools defined on the Fourier domain for the data that was on the Euclidean space, right? For images, for essentially voice. For those type of basically 1D and 2D signals, there are a set of conventional traditional signal processing tools that are defined in the Fourier domain. And then by defining this spectral domain as the analog for the Fourier domain, we can redefine those signal processing tools for the graphs as well. So including convolution. So the idea is that we have convolution in the Fourier domain defined for example, image processing. Now we can take this analogy and redefine convolution for the graphs, right? We can basically redefine convolution in the basically spectral domain of the graphs. Now, so we can write using these bases, we can decompose some function f defined on the nodes of a graph. And we can expand that using this eigenvectors. We can find the spectral representation of that signal, meaning that essentially a Fourier transform, a graph Fourier transform, which is taking the signal residing on the space of the nodes of the graph into the space of the eigenvalues of the graph. So we have our eigenvectors acting as our basis. So this matrix U is a matrix of different eigenvalues. Eigenvectors. So each column in the matrix U is one eigenvector of the Laplacian matrix. So Laplacian matrix is a square positive semi-definite matrix. It is V by V, so it has V eigenvectors. And then if it's connected, these are unique orthonormal eigenvectors. So if our graph is connected. So we take that matrix, transpose of it, we time that with the signal, it is going to take that signal and give you a spectral representation of that signal. So it is analog of taking an image and basically giving it back in the frequency space. So now in that frequency space, we can do some filtering. We can, for instance, we reduce or reduce basically the frequency, a particular frequency of the image and do some image processing on that and so on and so forth, right? So now we can do the same thing for the essentially inverse graph Fourier transform as well. So we can take these essentially these eigenvectors. Now this time not their transpose, but the U itself, we multiply that by the coefficients, meaning the spectral representation of the signal, and it will give you back the original signal. So it's gonna reconstruct the original signal that we have. Now, in the matrix form, you can see that F equal U times F hat. And here we are showing that in the index notation. So if you remember last session, we looked at the basically eigenvectors. We represent them on the graph itself. We saw that each eigenvector has one element corresponding to each node, right? And then we had multiple basically eigenvectors. We can basically go back to that slide at the end of the session. So now the main idea why we're redefining this Fourier transform for the graphs is that we want to redefine convolution for the graphs in the spectral domain. So like the case of the data on the Euclidean space, and it's basically the classic Fourier transform, we can also represent convolution as the element-wise product or the Hadamard product of two spectral representations of basically two signals, right? So we have, let's say, a signal F, and we have some filter H. We can take these, and these are defined on the graph, on the nodal domain of the graph. We can take these, and using this eigenvector matrix, we can project them to the spectral domain, right? So the convolution that we wanted to define, now it can be represented as element-wise product of the spectral representations of the signal and the filter H. Here, we're showing convolution using star sub G, which is representing a convolution for graph G. And the reason for that is that we're defining convolution based upon eigendecomposition of the Laplacian matrix. So Laplacian matrix is unique to each graph. It is not unique, but it belongs to that graph. So if I took the Laplacian matrix of the graph and use that for the Fourier transform, then what happens is that this operation is basically belongs to that particular graph. So I can use eigenvectors of a different graph for essentially doing the convolution in another graph. So that's why we have a G. It's showing that this convolution operation is happening on a graph G. This operator belongs to graph G. So now we said that we have this representation, and we said that this Fourier transform, graph Fourier transform UTH is taking some filter H, and it's projecting, it's mapping that to the spectral domain of the graph. So we can, just to be easier for everyone, we have a spatial domain. We have a spectral domain. We are defining so this spatial domain is basically defining something on the graph itself. So based off of different nodes of the graph, like when we were saying that we have a node, then its neighbors, meaning that we are defining it on the graph, right? So let's, for example, show that like this, and then we have a graph Fourier transform that takes some signal, some embedding that is residing on these, and it's representing that in the spectral domain. Spectral domain, I'm just showing that using, it is on here, indexed by different nodes of the, essentially, of the graph. And then on this axis, for instance, these are different frequencies that we have, okay? So different nodes, different frequencies. So we can use an inverse graph Fourier transform to take basically something defined in the spectral domain and project it back to the spatial domain. So when you're giving, for example, information of different people in the social network, that means that we're defining that on the spatial domain. Some operations, it's just easier. There's a whole class of tools in signal processing that can be used to analyze data, define on grids, for example. And we want to use the same tools that people are using for the graphs as well. So what we're doing is that we are defining some notion of graph, some notion of Fourier transform for graph in order to be able to take data that is defined in the spatial domain and then represent that using some essentially in the frequency domain, right? So
the coordinates of the spectrum.
There's no coordinates. I'm just saying that for each basically node, there is basically the total number of the eigenvalues is equal to the total number of the nodes. That's all I mean.
Okay, but
I shouldn't really write it this way.
you know, as far as I understand, when you do the Fourier transform, do the spectral space, the bases are the eigenvectors of the Laplace.
That's true. Yes.
Images.
Yes. So we have how many bases? We have V bases, not two. This is just, I'm just representing. This is nothing really. So, all right, again, we have this convolution defined. So we are, in order to do convolution of the data defined on this graph with some filter H, we are taking essentially, first of all, taking the signal to the spectral domain, then taking the filter that is defined in the spatial domain to the spectral domain. Over there, we just do a basically element-wise product of those two vectors. And then using U, we're basically bringing them back, this basically convolved signal, we are bringing the convolved signal back to the spatial domain, right? So we do the convolution in the spectral domain and we take it back to the spatial domain so that you can see it, all right? So now, so far we said that H is a filter and I'm taking that to the spectral domain. But that's not necessary. And in the index notation, so before going there, we're representing it as we have F hat, which is representing our spectral signal, spectral representation of the signal. We have, and it's defined on each, basically, it is indexed by the eigenvalues, right? And then I have H hat, which is the spectral representation of the filter, which again is indexed by different eigenvalues. And then I have U eigenvectors that I'm basically using to basically project the information back to the spatial domain. So now so far we said that we have some filter. So let's say that we want to apply some filter. We have, some convolution we define, some convolutional filter. We said that we define it on the spatial domain and then we project it to the spectral domain. But another approach to that is to directly define the filters in the spectral domain, right? So for instance, we have heat kernels. Heat kernel H hat is defined based off of as a function of the eigenvalues of the Laplacian matrix, right? And which is corresponding to some notion of the frequency. So essentially, this exponential of -5 lambda L is a basically frequency response, right? A basically filter frequency response. So we have L here, we have lambda here, we give it to some function, and this is gonna give me H hat of lambda, right? Now, using that, we are saying that for instance, we have some graph, we take that graph and find its eigenvalues, and then we give that to the function, this function, and for instance, this is this output is the response of this filter to these particular frequencies. And when we say eigenvalues of the Laplacian, usually we order them so that these are from basically in the ascending or descending order. Now I can take this and use the essentially inverse graph Fourier transform, and put it back on the graph. I can take this, whatever I defined here, I can take it using inverse graph Fourier transform presenting on the spatial domain, and that's how it's going to look like, right? So this is now this essentially filter H now is redefined in the spatial domain. So we can use that to learn filters. We can use that by directly writing ut of H as theta H. Now theta H is some parameter that we want to learn, right? So in the matrix, and it basically has essentially its dimensionality is equal to the total number of the nodes in the graph in this particular representation, because our original signal is defined that way. It's just a one-dimensional signal defined on the whole graph.